These are your video notes for section 2.7, which the topic is system of inequalities. Before we get into the system idea, which means multiple inequalities, we're going to kind of backtrack a little bit and talk about an equation, then a single inequality, and then we'll build that up to a system. So as some reminders, we need to start a little bit of investigation or discussion about solutions. And so I've got an equation of a line, y equals mx plus b, negative 3x plus 4. It's graphed right here. We've got 3 random coordinates. We're trying to check out some ideas about solutions or not. So using the graph, which of these coordinates is a solution to the equation? Now, to be in a solution to the equation, like it says here, we'd have to make the equation true, or just visually, it would have to be on the line. A point would have to actually sit right on the line. As I scan through the different coordinates here, I can see that negative 1, 7 is definitely on the line. But the others, which I'm not going to pop up just yet, negative 2, negative 3, just by visualizing, no, and 2, 3, no. So this is the only one that sits on the line. That makes it a solution. An alternative to just visually checking it out would be plugging it in. You can always check any coordinate to see if it's a solution to an equation by seeing if you get a true statement when you sub it in for x and y. In this case, we do. We get 7 equals 7, so now we know that's definitely going to be a solution. When you switch to inequality, then your coordinates have to satisfy the inequality, so they need to make this a true statement. And one way to do that is to test them. So let's take our other two, and by the way, let's go back to 7 to negative 1, 7. So the inequality reads greater than or equal to, and that means the equal to is still considered to be part of a solution. So the fact that I got 7 equals 7, that means this coordinate is a solution to the inequality as well, because it would be in the equal to category. Now the others we need to check out, are they making it true as a greater than statement? So let's go test negative 2, negative 3. If I plug it in, I get negative 3 greater than or equal to 10, which it's not. That's false, so that's no. That's not a solution. Plug in the other side, 2, 3, and I get 3 is greater than or equal to negative 2. That is true, so that is a solution. Now, the question really then is this the only one, or is there a bunch? Well, the thing is that actually this is like a test point. So this is like saying false, true. The true side, the true part of the problem will actually cover all possibilities over here. So we can now say which area of the graph produced the solution. So it's not a single point, it's actually any coordinate in this area, because they all would satisfy the inequality just like 2, 3 did. So when we're doing an inequality, it's not just about a single coordinate, it's about a whole collection of points. Like there's an infinite number of points sitting here that would all work in this inequality. And then the key here also is matching up symbols. So why is it a solid line and not a dash? And that has to do with the equal to part of it. And again, that ties back into the idea that the points that sit on this line are not just true in the equation, they're also true in the inequality, because the inequality has the equal to part of it. If it was dashed, on the other hand, then points that would sit on the line would not be included, because you would know equal to. Okay, that's kind of a quick flashback to the idea of just a single inequality and how we talk about solutions when we're looking at inequalities. Let's jump ahead to just another single inequality without all this extra stuff, and then we'll get into the systems in a minute. So things we're going to want to do is solve that linear inequality. We're going to want to get it graphed. We'll eventually tie the idea into some constraints, which is a little further down the road. Can we graph it correctly? And then interpret what's called the feasible region, which is the overlap of multiple shaded areas, and we'll get to that in just a minute. But still, let's just talk about single inequality for a couple more practice problems. There's something unique you got to be able to catch here quick before we get into the idea of systems, and that's what happens when you divide by a negative. So as you're working through this, you're just doing your normal algebra, move the 5x to the other side, and then you're going to go divide by negative 6. And anytime you do division by a negative, what it'll do is change the direction of the inequality symbol. That's an absolute must that you catch that, because if you don't, it'll cause you to shade on the incorrect side, and you won't really have the right graph going. Now, some things to pay attention to. Why is it dashed? Because of my inequality symbol again. No equal to symbol, that refers to dashed. Less than, as I read this left to right, this says y is less than. So less than would correspond to below. We don't really need to test points like we did in the first slide. That's certainly okay, but after you kind of get used to the visual aspect of it, we get used to saying that less than is below and greater than is above. So when I go to shade this, I'm going to shade below. That shading means that any point that I would pick in this area would be a solution to the inequality. Because there is no equal to symbol below this, the points that sit on this line are not solutions. So if I took this coordinate I've plotted here, or this one, and plugged them in, they would not satisfy the inequality. Okay, let's do one more single inequality, then we'll get the systems idea going in a second. So a little bit just more practice with cleanup. So cleanup means get into y and then mx plus b. And then the inequality also as you'll work through. So here's a little bit of distributing. Get my y alone on one side. Here's division by a negative. So one more reminder that division by a negative changes the direction of the equality symbol, and you got to catch that, right? That'll definitely affect your final answer. And then tying stuff together, so greater than or equal to is going to be a solid. Greater than is going to mean I'm above. So again, that both of those would be things I want to consider before I start. And then which side am I shading on? Above that line, which is up here. Again, this means every single point that sits up here is a solution to this inequality. It would satisfy it. It would make it a true statement. Okay, let's talk about some unique kinds of lines. We will get into systems in just a second, I promise, but vertical and horizontal, so which one's which? And hopefully you guys have got this down from your geometry days, but again, y in a number is horizontal, x in a number is vertical. The idea being that actually is a line, every y value on this line has a value of 3. Every x value on this line has an x value of -2, and that's what causes it to be horizontal or vertical. Just getting the line graph is simple enough. Again, I'm using solid because of the equal to symbol. We'll go over here and kind of do side by side. So -2, I'm using dash because of the not equal to symbol. And then where do I shade? So when it's a y, a horizontal line, above and below still works really nice. So less than would be below, greater than above, so I'm less than below. When it's x, you have to actually think of it as left and right side. So which numbers are bigger than -2 on the x-axis? That'd be this way. Less than -2 this way, so I'm actually shading to the right. So vertical is the one unique one where we ask ourselves left and right. Every other kind of line is above or below. Okay, and these pop up in your system sometimes, so again, we got to be clear on how to include that as part of a system of inequalities when we need to. Well, we're getting closer. We're still not quite to the system yet, but one last problem before we do that, which is, can you work the problem in reverse? So from what you see, can you write the inequality? I think some of the easy stuff is going to be in getting your equation ideas ready to go. So what's your slope and your y-intercept? So 2/3 slope, I'm just counting from point to point, and a y-intercept at -5. And then when I go to write my inequality, not an equation right now, an inequality, I look at the shading. So solid and above. Well, solid and above should be a greater than or equal to, and there's my mx and b. Over here, I've got a slope of down 1/2, -1/2, a y-intercept of, tied out somewhere, there we go, 4. It's dashed and I'm below, so dashed and below would be a less than. And then mx plus b. Pretty easy to do there. I mean, that's just all visual kind of stuff, and it shouldn't take you much to figure that one out. All right, so finally into a system. Now, a system's going to be a little bit different. I'm not going to read through all the points on this slide to you guys, but the basic idea is that you have to shade multiple times. And when you shade multiple times, that means there's going to be an overlap. So multiple inequalities, multiple shading. The overlap area we call the feasible region, the common shaded area, and that's the one thing we're going to want to focus on. All right, let's get started. So before you get going, it's a good idea to do y mx plus b. And then where do I shade? Now when I do this, I kind of like to start by just doing some sort of arrows to kind of help me visualize a little bit. So this reads less than, so less than's below. So if less than's below, that would be here. This one greater than or equal to, which is above, which that would be here. And so I visualize like if I was shading below the red, then above the blue, where would the shading overlap? And the overlap is what I actually want, and that's here. That's what's called our feasible region. That means the area where your solutions could sit in. So it's, again, really, I don't really do shade and then shade. I visualize those, and then I just shade the overlap. Now, as far as this coordinate being a solution, that's just a test idea. So if I go and plot 4, -5, 4, -5 sits right there. And the fact that that point sits inside of the feasible region means it's a solution. So it's a yes. Simple enough. If that coordinate's in this area, it's a solution. If it's anywhere like here, here, or here, it's a no. If it sits on the line because it's blue and equal to, yes. If it sits on the dashed line not equal to, no. So there's those details. Typically, we're going to ask you stuff about something out here in the feasible region. Okay, pretty simple system to start with overlap shading. So now a system of 3. And so we'll get those graphed up. So I'm just going to pop them up quick. You know, we're just working off of y-intercept and slope. Y-intercept and slope, and also the same. Now again, before I go nuts shading all over the place like crazy, I just like to do a little bit of arrow. So if I'm less than, I'm below the blue. I'm less than, that's below the red. I'm greater than, that's above the black. Now again, if I visualize that as multiple shaded areas, I'd be doing this. I'd be shading all of this, then I'd be shading all of this, then I'd be shading all of this. And it's like, again, you got to try to visualize the best you can, but that actually produce a feasible region that sits right here. So that's the area of solution, which means any point in this area satisfies all three inequalities. And that's the key here, is that it's got to satisfy the entire system. So I pick a coordinate in here and plug it in, it's going to be true, true, and true. I pick a coordinate out here, for example, it might be true to one of them, or two of them, but not all three. So in the feasible region, everything in there satisfies every single inequality. So for example, how about the coordinate 2, -1? Well, if I do 2, -1, that point sits right here. And that is in the feasible region, so that's a yes. Other things we like to look at besides just points that sit inside are things known as vertices. A vertex is actually points of intersection as you travel around the border of the shaded area. So imagine you like walking the path. Every time you hit an intersection, that's going to be a vertex. So there's going to be one at 0, -2, at 2, 2, and at 4, -1. Those spots right there, again, along the border of the shaded area. Now, in terms of them being solutions, the ones that are on the solid intersection, yes. But to the system, no. That would not satisfy. That would not satisfy. Okay. And that is basically it